Let's go. Okay, so yeah, nothing new here. Just doing reversing again. Um, all right, who am I? I'm Sharad. I'm fourth year here. I'm from. Thanks, man. Really appreciate it. So I'm from Northern Virginia. I currently work at 2.6 as a vulnerability researcher. I was previously at Zelic, which is a real silly company, and a company called High Peak Cyber, which is now part of a company called Magnet Forensics. All right, so what is reversing? Reversing is basically the process of taking something that you don't know about, basically a black box, and trying to derive some information from it. So it doesn't necessarily have to. So usually it's a binary. When it be the binary, it's like an executable or any program that runs on your computer. That's usually what you reverse engineer. There's a lot of tools to do that, but it doesn't really have to be that. Some very common things that people reverse engineer in the industry is stuff like protocols, executable formats, storage formats, hardware. Basically anything you don't know about can be reverse engineered. Today's presentation is more going to be about binary reverse engineering and how to reverse engineer an executable. All right, why reverse at all? Reverse engineering is a pretty important part of a lot of like disciplines in cybersecurity, both offensive and defensive. Reverse engineering is very useful in IR, especially when you're doing stuff like EDR development and you need to build out detections for certain pieces of malware. To build out how to detect that piece of malware, you obviously know how that malware works. So you need in that case, you need a reverse engineer to figure out how that malware works. Being capable of reverse engineer is also really helpful when you're doing stuff like vulnerability research. When you're doing vulnerability research on just like a closed source target, you need to have an understanding of, well, I guess to find a vulnerability in a piece of software, you first need to understand how that software works. And to understand how that software works, you need to essentially have a reverse engineer who can tell you how that software works. So yeah, it's useful on both offensive and defensive sides. So it's a pretty important part of cybersecurity. So how do you be an effective reverse engineer? It's mostly a mindset thing. It's just like practice and mindset. It's just, yeah, I mean, like, from what I've seen in reverse engineering, the most effective reverse engineers know how to, they know about what to, I'll talk about this later in the presentation, but they know how to not get caught up in stuff. That's a really important part of reverse engineering. And yeah, I mean, like, that's a really big part of it, not getting caught up on stuff. Other stuff is like the ability to target research. Being able to look at your software, identify what it is, and identify where to get the proper information on your target. So for example, let's say you have like a microcontroller and you just open it up. You're trying to reverse engineer what the microcontroller does. Being able to essentially know the next steps and know, like, okay, let me go find some serial numbers or some numbers on the PCB. Let me go look it up, find the data sheet. That kind of process and and having practice in that is what makes an effective reverse engineer. It's really the same thing with also software reverse engineering. I think I displayed this a lot more in my Flare presentation, where I talked a lot about mainly target research. So that kind of stuff is really important for being a reverse engineer. And on top of that, obviously having knowledge of stuff like assembly and all that stuff is really important. So an effective reverse engineering mindset, I kind of talk about it more here, but I've always found the idea of like footholds to be pretty interesting. Basically, a foothold is more just like it's a portion of a system that you understand, a portion of the system that's like well known or well understood. So for example, a normal executable, you might see stuff like exported functions, stuff like, I don't know, like let's say there's like a call to like printf here, right? That always has to be there. So knowing that that's there and seeing that and working backwards from that is really effective. When I was reverse engineering ARM hypervisor, the address of vbar el2 was really helpful. That's the hypervisor exception table. Not gonna get too much in the internals of that, but depending on your system and understanding, like, I guess understanding your target, you'll basically know what these footholds are. And basically these footholds serve as essentially entry points through which you can eventually gain more information. Again, don't get stuck on the small details. If you don't understand what like a few assembly instructions do, it doesn't really matter most of the time, unless you know it matters. In that case, you should probably focus on it. And the final thing is pattern recognition. Pattern recognition, You'll see that a lot when it comes to like certain patterns. For example, over time, as you reverse engineer more, you'll see that you'll eventually kind of innately know what's like a struct access versus what's an array access. Like whether the struct is on the stack or the heap, stuff like that. Being able to recognize those patterns is really important, and the only way you can really get that is just like practice. All right, so some reverse engineering terms, static analysis. I know the 202 class goes over like basic and like advanced static analysis. That's like not real. Never really has been real. I don't really know why they talk about that. There's like static analysis, but just like looking at the binary without running it or loading it. That ranges anything from like strings to like loading into like Gidra or IDA or Binja. It's much safer. It's much easier. You don't actually have to run it. And oftentimes running it can be like damn near impossible, especially for stuff like firmware. You just can't run that without like a substantial amount of effort. So oftentimes static analysis is like your only route. But the main disadvantage with it is that a lot of pieces of malware, a lot of pieces of software these days come with anti-static analysis techniques, whether that be stuff like anything from LLVM-based obfuscation, like control flow flattening, all the way to stuff like Packard's self-decryption, stuff like that. Yeah. In other cases, static analysis is like pretty impossible for stuff like firmware, because stuff like firmware that often interacts with like vendor-specific peripherals. So not being able to, if you look at that in a pure static context, it's very, very hard to decrypt and really very, very, very hard to understand what that's doing. All right, so the other side is dynamic. Dynamic analysis is analyzing a binary while it's running. It's nice because you can just see what the binary is doing in real time. You can see the inputs and outputs for functions. You can see, okay, that it's making this call here under this context. Yeah, and if in the case if it's obfuscated, dynamic analysis can often help you remove some layers of obfuscation, especially in the case of stuff like packing. That just kind of dynamic analysis for the most part just kind of defeats packing if you know what you're doing. The disadvantage is you actually have to run the binary. Again, that can be hard in a lot of cases. Yeah, and so oftentimes dynamic analysis is not feasible, or that be, and I guess there's also ways to prevent dynamic analysis with stuff like anti-debug. There's actually a demo on that, and just some minor anti-debug stuff. So yeah, I mean, there's a lot. Dynamic analysis can be very nice, but there's oftentimes a lot of challenges associated with actually getting dynamic analysis to work. All right, so I'm just going to intro to assembly and x86 real quick, and yeah. All right, so about x86. x86 is a CISC architecture. It's a complex instruction set architecture. It's mainly used in PCs. Yeah, I mean, these days, a lot of people are moving to ARM, though. Stuff like M1. I know AWS has introduced like their Nitro. I don't know if it's called Nitro. I forget what it's called. I know AWS made their own proprietary ARM chip. It's a very old architecture. It's from like the 80s. So there's a lot of just like iteration that's happened on x86. There's three main modes: real mode, 16-bit, 32-bit mode, which is protected mode, and 64-bit mode, which is long mode. And you kind of have to boot through all three modes. It's kind of annoying as hell. If you come to VRig, you kind of know that we've spent way too much time on this. But yeah, I mean, so yeah. So x86 instructions are always in the format of your mnemonic, which is the name of your instruction, the destination operand, and the source operand. The destination and source operands can either be registers or memory, or in certain, yeah, pretty much registers or memory. Can't think. I think there's other cases, but I can't exactly remember them. Predominantly though, registers and memory are going to be your operand types. So registers are on CPU memory, and they contain values used for computation. So there are, at the bottom here you can see the registers that we have. Basically, the registers are split into basically subdivisions of powers of 2. So the highest power of 2 is an 8-byte register. So RAX, RBX, RCX, RDX, RSI, etc. Those are all 8-byte registers or 64-bit registers. The lower half, the lower 32 bits, meaning the least significant 32 bits. I'll explain what that means when we get more into like examples of assembly. But the lower 32 bits of assembly are all of, a register are going to be the E registers. So it's going to be the 32-bit registers. So EAX is going to be the lower 32 bits of RAX. Yeah, the lower 32 bits of EBX. I guess EBX is the lower 32 bits of RBX, etc. You also have 16-bit registers, 2-byte registers, AX, BX, CX. Those are the lower half of EAX, EBX, ECX, etc. You also have the 1-byte registers, where it's like AL, BL, CL, DL, etc. Almost all instructions require the use of some kind of register. Yeah, I mean, I don't think there's any real exceptions to that. I think there's actually it's like there's like the rep instruction, but even that uses registers. But yeah, I mean, you almost always need registers for pretty much everything when it comes to CPU operations and assembly. All right, so memory. Unfortunately, we have a limited number of registers, so we can't put everything in. We can't put everything in just registers, all the values we need. So we do need to put stuff in memory. So memory is just like I don't really know. It's kind of just like a big data bank that just stores values, just stores bytes. Conceptually, you can imagine memory as basically an address, basically just a map where each address maps to a single byte. Yeah. Let me move to the next slide. So this is a quick memory visualization. This is how an Intel CPU sees memory. There's actually a really nice diagram that I found earlier. I'm not really sure why nobody's. I don't know. It's just a really nice diagram. So. All right. So there are. Do I go to the next slide? I do. Okay. So yeah, this is how memory works. On the left-hand side, on the numbers on the left here, those are the addresses. And at each of those addresses, you have a single byte. The H essentially just represents it as a hex number. So that's 0 as hex, 1 is hex, 2 is hex, etc. Yeah, so as you can see, every address maps to a single byte. So this actually goes into a concept we'll talk about later, which is endianness, but I'm not talking about that yet. All right. In memory, so in x86, you can access memory in 4 different ways. You're going to access memory as a keyword, a dword, a word, or a byte. A keyword pointer essentially means you access 8 bytes starting from. So I guess real quick. Yeah. So shit. So I guess real quick. So when you try to address memory as an operand, when you try to use a memory operand essentially, which is basically just you try to access memory, the way you represent a memory operand is using this format right here, this size and address format. So the size represents the size of how much you're trying to access, and the address just represents the address you're trying to access. So a keyword pointer essentially just means so the size has 4 sizes. Actually, there's technically 5 sizes now. There's keyword, dword, word, and byte. There's also x and m word, which is 16 bytes, but that's not really used very often. So keyword means you access 8 bytes starting from this address. Dword means you access 4 bytes starting from this address. Word means you access 2 bytes starting from this address here. And byte means you access 1 byte starting from this address here. What that functionally means for I guess what that really means in practice is you get something that looks like this right here, where, for example, let's say you want to access the keyword at the address of 6. The value you'll get is this value right here, which is this value rather in little endian, which I'll talk about a little later. You'll get this value right here. And if you want to access a dword, which is a double word, you'll get this value. If you want to access a dword at the address A, which is 10, you'll get this value. Want to access the word at this address, you get these 2 bytes here. Want to access the byte at this address, you get the 1 byte here. So in that sense, yeah, I mean, that's really how memory works in x86. So a key instruction in x86 is move. That's how you move between registers and memory. So there's really 3 patterns for move that exist. There's you move between 2 registers. You move between a register and a memory. This is what's called a store, because you're storing this register in this memory. And you move from this memory into the register. Those are the 3 main formats for move. Yeah, I mean, yeah, that's pretty much move. All right, so endiness, real quick. So whenever you store and load from memory, you always store and load. Well, the idea, I guess, behind endiness is that when you store and load from memory, I guess when you store and load multi-byte structures from memory, so let's say you store an 8-byte integer to and from memory, there's basically two orders you can put it in. You can either store it as little endian, meaning that when you write the address to, because keep in mind, memory, each byte has a, rather each address is associated with a single byte. So you can basically write the number in two ways. You can either write in little endian, meaning that the lowest address has the lowest byte, or you can write in big endian, meaning the lowest address has the highest byte. x86 is pretty much always little endian. There's no exceptions at all to that rule. Other CPUs like ARM can switch between big and little endian, but x86 does not do that. I guess this diagram actually describes endiness really well. So if you want to access, so for example, if you want to access a keyword at the address 6, these are the 8 bytes that you get here between 6 and D, 6D being 13. If you want to access that keyword here, you access it in little endian format, meaning that this B is the least significant byte, meaning it's the lowest byte of the number. Then 23, then AH, then 1F, then 36, then 6, then FE, then 78. You kind of see that reflected in the number here. The least significant byte is B, which is here. Then the next byte is 23, which is here. The next byte after that is A4, which is here, etc. So, I mean, that's basically how endiness works. When you access the least significant byte is at the lowest address, which is here. All right, real quick, the stack as well. The stack is pretty important. Pretty much every program needs a stack to operate. The stack is basically where all temporary variables are stored. Any variable with like scope. Every function gets its own stack frame, and the stack grows down. The stack grows down mainly because we always put the stack. It's just kind of a convention. We always put the stack at the highest possible user space address, and then we always grow down. Do I have that diagram in here? Or no, I guess I don't. But usually we put the stack at the highest possible addresses. We put the heap right below the stack. So the stack is going to grow down. The heap is going to grow up. So we're going to grow towards each other. That's just kind of a convention. So the bottom of the stack frame. So there's two registers that kind of determine your stack. There's RBP and RSP. The bottom of your stack frame is determined by the base pointer, which is RBP in x86. And the top of your stack frame is determined by the stack pointer, which is RSP. The bottom would the top of your stack frame is RSP, and the bottom of your stack frame is RBP. The top of the stack frame is basically where all your newest values are, and the bottom of your stack frame is where all your older values are. Almost always, unless RBP is being used for something else, RSP is always going to be less than RSP. I mean, RSP is always going to be less than RBP because the stack grows down, RSP is going to be slowly growing down, therefore has to be less than RBP. What the fuck? So there's many two operations we use to interact with the stack. There's push and pop. Push just pushes onto the stack, so that essentially subtracts 8 from the stack pointer from RSP and moves a new value into that new area. To pop a value, use pop. That just pops into a register. That essentially moves 8 bytes from RSP into the register and then adds 8 to RSP. All right. So when you call and return functions, there's many two instructions. There's call and there's return. Call is basically a combination of two different instructions, which is push and jump. So real quick, jump is a pretty simple instruction in x86. All it really does is just jumps to a different location in memory. By default, all instructions will run in order, but using jump, you're essentially able to jump to a new portion of the code. So jumps are mainly used for stuff like if statements or for loops, stuff like that. call is basically an expansion upon jump. Call is a combination of two instructions, which is push and jump. It pushes the return address and then jumps to the location of the function. Yeah. And then when you want to return from a function, you always ret. Use the ret instruction. Ret is basically just a special pop. All it really does is it just pops from the current stack pointer and it goes back to the. It just kind of just jumps to that location that was in that. I guess jumps to the pop location is probably the way to say it. So typically, what you'll do, I guess, am I going this later? Yeah, you go into the function prologue and epilogue. But typically, to essentially kind of, because basically what you want to do is you always want to ret the ret and pop. I guess when you're returning, you always want to pop the address that call pushed. So to facilitate that, they have a function prologue and epilogue. The prologue basically, the way that works is it saves EVP, and then the move EVP ESP essentially sets up a new stack frame, and then you sub ESP by n. That basically just sets up the new stack frame for the new function. I don't know why the prologue and epilogue shit got cut off, but so when you want to return from a function, you always run the epilogue. The epilogue, what that does is it moves EVP into ESP. That essentially resets this instruction here, and you pop EVP. That essentially reverses this push EVP, and then you ret. So the idea is that right before this push EVP, the return address was pushed. So when you ret, you should be returning, should essentially be popping the return address that call pushed. Now the key idea is that you can actually exploit this quite easily. If you're able to overwrite that that return address using an attack like a buffer overflow, you can essentially get control over how the program is running. Yeah, and that's kind of the key, because if you can overwrite the return address that ret will pop, then that means you can control where it rets to, and that gives you control over the program. So that's basically the idea behind a buffer overflow and a lot of memory-based attacks. So calling convention. So when you call a function, oftentimes functions do have arguments, and when we want to essentially call a function, we need to set up our arguments in a certain way. And that's what calling convention determines. Calling convention for x32, so 32-bit x86, the way that works is you always push the arguments in return order. So let's say you have a function that has an int and like a long, for example, as its arguments. You'll always push the long first and then push the int later, because that's just kind of how it works. Yeah, because you always push the last argument first, and you always push the first argument last. Yeah, so you kind of see that here, where the first argument is lower on the stack than the I guess the last argument. 64-bit calling convention is a little easier. You just kind of move your arguments into registers, and any overflow, any additional arguments are always pushed on the stack. So for any Unix-like OS, like Linux, they always use this calling convention right here. Your first argument's in RDI, your second argument's in RSI, your third argument's in RDX, etc. If you exhaust those registers, you always push arguments onto the stack. With Windows, you essentially do RCX, RDX, RA, R9, and those are your 4 argument registers. Any additional registers are essentially pushed onto the stack as well. Yeah. All right. I guess I was doing a stack demo. All right, let's just do a demo real quick, because like I don't like talking about that. Yeah. Run the clear command? No. Yeah. What? Not to ls again. Okay. All right. Let's like rip this. Yo, I just did anger. What the hell? What was I doing? All right. You know what? We're just gonna. All right. Oh shit. Those are leaks. We are not doing anger. We'll just like create this file here. All right. Okay. Let's see if I remember anything about how to write assembly. All right, so let's do like start. All right. So at this point, I'm just like kind of writing us an example assembly file here. Example.o, example.s. Oh, that actually worked. That's ridiculous. File. Okay. Yeah, is always be relocatable. Cannot find. Okay. God damn it. How do you? Oh yeah. There we go. All right. So. Out. All right. So I guess it's also like technically just like a GDB tutorial as well. Now that we're here. So I guess. So when you're doing dynamic analysis, you will often want to run it in a debugger. A really good debugger that I like is GDB. That's pretty much the main debugger for Linux. GDB kind of sucks ass though by default. So to make it better, you often use GDB extensions. This right here is Pwn debug. You can just kind of find it online really easily. Just look up Pwn debug. Just look up Pwn debug here. Just kind of download it. It's pretty easy. Wait, what? Okay. Anyway, that's kind of cool. Anyway, so basically, it's very nice because it just kind of shows you a description of everything. For an entry here, you'll see that we have a full description of what the registers look like. Usually we also have we have a full description of the registers, the assembly that we're looking at, as well as the stack. That makes working with GDB a lot easier because if you don't do this with GDB, you just kind of see nothing every time you run GDB. So yeah, it just makes your life a lot better. All right, now that I know that that's working, let's write some actual assembly. Where is my code? There we go. All right. So let's start with move. So move, simplest instruction. So one thing you can do with move is you can move an immediate. An immediate is just a regular number into a register. So you can move, for example, I don't know, ox dead beef into RX. So if I run this, if I compile this here, and I GDB it, we'll see that if I run entry here, like here, I run that instruction. So essentially, to go to the next instruction, I guess let me show it again here. So go to the next instruction in GDB, you always run ni, which is next instruction. There's actually two instructions to do, is si and ni, step into and step over. So when I run that instruction, you'll see that Rx now contains ox dead beef, as you'd expect. You can also do the same thing with, you can also move between registers. So for example, do that, I can move between RBX and RAX here. What that does is it will not change the value in RAX at all. The value of RAX will remain the same, but it'll essentially copy the value of RAX into RBX. So again, RAX will not change. It'll essentially, by the end of this, RDX will, RBX will equal RAX by the end of this. So recompile that. That's not what I want to do. So if I do this, at this point, again, RX contains dead beef. And RBX, at this point, when I run this instruction, RBX should also contain dead beef, which it does. They both contain dead beef. All right. So let's write. So now we have this. Suppose you want to put, I don't know. Suppose you want to put dead beef in memory somewhere, right? So for example, let's say we want to push RBX. This right here will push, because RBX at this point now contains dead beef. This will push ox dead beef onto the stack. So we'll see is that we will see this RSP value be decremented by 8, and in the new space that was created in that, I guess, the section between RSP and RSP minus 8, we'll see the value ox dead beef. Shit. How much time do I have left? 12:45. Okay. So as you can see here, actually, let me run that. So at this point, RBX contains dead beef. We'll push it. So we'll see that this gets decremented by 8. So right now, RSP is, I guess it ends on 390. So we'll see that when I push, we'll see that we get decremented by 8. Keep in mind these are hex values. These are not decimal numbers. So that may not be working the way you expect it to. Yeah. So that subtracts by 8, and we'll see the new value at RSP is ox dead beef. If we print out the value at RSP, print out the 8 bytes here, we'll see that this is essentially ox dead beef in little endian. So we see that the EF is a least significant byte, so it's at the lowest address. Then we have the BE, then we have the AD, and then we have the DE. So we'll see that this was actually in little endian. All right. Let's say I want to pop it into RCX. Pop will essentially move from RSP into this register here, and then we'll add 8 to RSP. So let's look at that. So this point, again, we're here. We've pushed ox dead beef onto here. So we should see after this that this should go back to to 390 here because we add 8 to RSP. And we'll see that this value right here is then moved into RCX. So we'll see that all 3 are now RCX, which is cool. So that's push pop. All right. Let's say I want to call a function. Actually, let me do a move from memory. Suppose I want to move a value from memory here. So at this point, I push RBX. Let's say I move from D word RSP. Let's say I move, in this case, I'm moving a D word, so moving 4 bytes starting from RSP into EDX. Let's say do that. Oh, what the actual fuck? What the actual fuck? Okay. So at this point, we have ox dead beef. We're going to move 4 bytes starting from RSP into EDX. Keep in mind, this is going to be moved as little endian. So if I want to print this out real quick, move the 4 bytes starting from RSP, it's going to be EF, BE, AD, DE. We turn that into little endian. So that means that we essentially have EF is going to be our first byte, then BE, then AD, then DE. So we're essentially going to see ox dead beef moved into EDX here. So we're going to see by the end of this, RDX now contains dead beef. All right. So, all right. So that's how you move from, and I guess do the same thing when you move to memory. So let's say I want to move, I don't know. Say I move, I don't know, EDX. Say I move into EDX, I don't know. 1 1 2 2 3 3 4 4, and I want to move into RSP. Move EDX into RSP. So we'll see at this point that EDX now contains 1 1 2 2 3 3 4 4. We move this value into these 4 bytes into RSP. So we see that that this value right here, again, this value right here, move 4 bytes. So this value should change to the value in EDX as little endian. So we should see by the end of this that this should be 4, because it's the least significant byte, then 3, 3, then 2, 2, then 1, 1. So we see, we print that out again, we get 4, 4, 3, 3, 2, 2, 1, 1. So that's kind of how you move to and from memory and to and from registers. All right. So let's talk about jumps real quick. All right. So when you want to call a function, call a func. Right? Let's say I want to move. Also, I forgot to mention this, but your return address, your return value always goes into RIX. It's just kind of how it is. So if I want to return 0 from this function, I move 0 into RIX. If I want to return, I don't know, 3, I move 3 into RIX. And then I ret. So all this does is just the equivalent of return 3. So let's say I call func A. We see that. Okay. Yeah. So we should see that when we call func A, we should see the return address. The return address is always going to be the next instruction. There's going to be this value right. We're going to see that this instruction right here, this address right here rather, is going to be pushed. So we'll see that on the stack. See 8 bytes decremented from the stack, and we'll see that this value is pushed. So I go to step into this function. We see that that address was pushed here. This address right here is pushed, and we see that, yeah. So in this case, I move 3 into EAX. We see that 3 is an EAX. I'm going to return. So what return is going to do is going to pop this instruction. Is going to pop this address off, and RIP, which is the instruction pointer, is now going to be contain this address. So we'll see that here, and RIP now contains this address. That's kind of functions. I guess real quick, one that could be fun to do is just write an if statement. So in assembly, there's also like conditional jumps. So you can jump based on a condition. Those are mainly used to implement stuff like if statements, for statements, while statements, etc. So suppose I want to make the if statement where, I don't know, that's a really, okay, I'm not gonna do that. Suppose I want to make this if statement where I have like if A is equal to 0, then return 3, else return 4. It's a real simple if statement. I'll make this here actually. Yeah. So in this case, suppose A, I don't know. Suppose int func A. Because you have, I don't know, you have int A as your argument. Suppose that's your function, like your real bad function in C. So in this case, so we put everything that we know together. We know that the first argument of the function is always going to be in EDI or RDI, because that's simply the calling convention that we use. The first argument is always going to be in RDI. So what we're going to do is we're going to compare. A compare instruction just compares two values. We're going to compare RDI. RDI is the first, again, RDI is the first argument, so it's going to contain A. So RDI is going to contain the value of A. Compare RDI with 0. If it is 0, then we are going to, I guess, in this case, we're going to jump equal. We're going to say equal is here. We're going to move EAX 3 and ret. Jump equal. Move EAX4. So this is kind of how you implement that in assembly. Really what's going on here is again, the value of RDI contains A. We compare A with 0. If A is equal to 0, this jump equals right here, essentially works off the value and the results of this compare right here. If these two values are equal, then we jump to equal here. Then we move EA3 into EAX. Again, EAX is going to contain a return value. So in this case, by moving 3 into EAX and returning, we therefore return 3 when RDI or A is equal to 0. I should probably return here as well. But if it's not equal, then it's not going to take this jump because it wasn't equal. Because again, JE is jump if equal. In this case, it's not equal, so it goes here. Then it moves 4 into EAX, and RETS, so that's the equivalent of returning 4. So if I call, if I move, I don't know, I move 0 into RDI, then I call func A here. Func A. We'll see that when I compile this, I got like 5 minutes left. See that actually Pwn debug nicely shows us here that the first argument, RDI, is 0. So that's cool. So we see that when we compare RDI with 0, this compare should succeed. We see that Pwn debug is telling us that it does succeed, so it's going to take this jump. Then we are therefore going to return and move 3 into EEX, and then we're going to return. So by the end of this, we should see that in this add here, I guess when we return from the function, we see that we've now returned 3. If let's say I move, I don't know, 1 into RDI, we'll see that this should fail and return 4. So we'll see that see up here, RDI. Wait, what? Oh, I forgot to wait. What did I forget to recompile? Oh, I forgot to save it. God damn it. So at this point, the first argument is now 1. We step into, we compare. We see that this jump it's not showing us a check mark here, meaning this jump has failed. So we go here. Again, this jump failed because 1 is not equal to 0. So we go here. We move 4 into EAX, which essentially returns 4. So at this point now, we've now returned 4. So this kind of just is a really basic example of how you can take C and how kind of that reflects in assembly. Have anything else? I didn't even finish my slideshow. Anything else in here? Oh shit, I talked about all this. You know what? We're just gonna skip all this. Okay, let me talk about the heap real quick. Not gonna lie, I made this presentation last year and I just did not look at it before I presented this. All right, so the heap is used for non-scoped variables. It's typically used for containing variables that you want to persist after a function returns. Because typically, if you put variables on a stack, those are all temporary variables. So those variables when you return from a function, they always clear and you can't access them anymore. Heap, you can't access them, and that's kind of the point of the heap. The heap must be explicitly malloc and freed. It must be explicitly allocated and freed. That results in a lot of issues, especially in improper usage of the heap. Sometimes if you free early, you get a use after free. Sometimes you'll free twice. You get a double free. Memory leaks, which means you just don't free at all. So using the heap properly is a very, very contentious issue. There's been a lot of solutions to it over the years, whether it be garbage collection. In recent times, you have stuff like Rust, which has the borrow checker, which is like automated heap management. So over time, people have come with quite a few clever solutions to handling this issue. I literally just did that, so I'm not going to do that. All right, so some useful reverse engineering resources. So crackmes, those are just like a bunch of reverse engineered, small binaries to reverse engineer. VX Underground, that's mainly a malware related site, contains a lot of papers about malware and malware development resources, as well as malware development samples that you can reverse engineer. If you ever do 202, you'll probably end up using this site. The reverse engineer public Discord, that place is kind of a cesspool, but sometimes there's useful shit there. There's also this site right here, the Felix Clouder site. That is just an x86 AMD64 instruction set reference. If you ever see an instruction that you don't recognize, or you see a version of an instruction you don't recognize, it's very useful hitting here. You often see behavior that you don't. I know we use this a lot in VRIG, especially when we're diagnosing a lot of behavior that we don't understand. Some instructions have very odd behavior, so this is often very helpful. They have very. I guess I'll show an example of this, but I don't know. IRET, right? That's not what I wanted. There we go. So for example, they have very nice full operations, which just basically describe exactly what the instruction does in very, very high detail. So if you ever see something you just don't understand why that's happening, awesome resource right here. And of course, the Intel manual. If you care enough to read that, you'll see a lot of really, really nice shit in there. Just some useful stuff. I think that's it. Any questions? Thanks, Maxim. All right. Thanks for listening. All right. Yeah, what do I do? Oh, you do have a question. What's up? What's up, Seb? My favorite x86? Move APS. No, I'm just kidding. Actually, let's look. Let's look at some real vile ones, shall we? Or like this one, GF2P8 affine in. Wait, why is this a thing? It's actually kind of nice. Wait, this is a real instruction. That's kind of nice, actually. That's a kind of cool instruction. Yo, this is for RSA actually. Oh, it just has like the polygon. It's just like the RSA field. That's it. Not the, I mean, yeah. This is the This is the AES field. Yeah, this is the AES GF128 field. Yeah. Pretty much, yeah. What else is like a vile instruction? Yeah, it's just like what the actual shit is this? Like yo, fuse, multiply, alternating, subtract, add. Yeah, I might as well. You know what? Yeah, let's move on with our lives. Yeah, yeah, real mad. Yeah, Max. So you want to get up here and explain what that is? All right, there we go. I don't know. I kind of hate all of them. I'm not gonna lie. Yeah. Yeah. Okay. I don't know. This is just like every single x86 instruction. No, what they do. No, he basically just made a script. The Intel manual actually just has all of them. Um, do I have it open? I just do have. I was actually reading this earlier. Yeah. So you can actually find all the descriptions here. And he pretty much just like rips them from here, I think. Just automate. Yeah, you can see all of them here. I don't even think that contains all of them. Yo, what is this? What is this? Like, this is like not a real. This is like not real. Like, this is like actually just like this is actually like woke liberal nonsense right here. It's like not a real instruction. Okay. No, I can't say I had. Any real questions? That was not a real question. All right. All right. Cool. Thanks for listening.